So now we will see the determination of acceleration due to gravity using a bar pendulum. So we've already seen a compound pendulum. Bar pendulum is a simplest form of compound pendulum where we use a metallic bar as the oscillating body, and this the bar shown in figure is a symmetric compound pendulum. Is an example of a symmetric compound pendulum since its center of gravity is exactly at the center of the bar, that is at half the distance from one of the ends, and the bar is suspended from a horizontal knife edge which can be inserted into any of the desired holes. So we have a lot of holes here which will give different values of time periods of oscillation. Now the determination of G using bar pendulum is based on the interchangeability of the center of suspension and center of oscillation. We've already seen the interchangeability of center of suspension and center of oscillation in the case of compound pendulum, and the 2 points, the center of suspension and center of oscillation, can be found at unequal distances on either sides of the center of gravity so that the periods of oscillation t about them are equal. As we already know about these 2 points, center of suspension and center of oscillation, we will have the same time period. In this figure, we have the center of gravity here. So as we have seen in the compound pendulum, this should be somewhere here. There should be a point of or center of suspension, and somewhere here below G there should be a point of oscillation, and both these points will give the same time period of oscillation. Now one of them will be at the center of suspension and the other will be the center of oscillation, and the distance between the two will be the length of the equivalent symbol pendulum. So we have already seen that the distance or the length of the equivalent symbol pendulum is given by the distance from point of suspension to the center of gravity plus the distance from center of gravity to the center of oscillation. The total length is given is the length of the equivalent symbol pendulum. Now, since we know T and capital L is the length of the equivalent simple pendulum and T is the time period, the acceleration due to gravity can be determined using the relation G equals 4 pi square L upon T square. This equation we have obtained from the equation of time period, which we have already seen in the last class. The time period of the compound pendulum was given by 2 pi root over capital L upon G, where capital L is the length of the equivalent simple pendulum. We just squared it and wrote the expression for G. Now the experimental procedure. The bar is allowed to oscillate about the horizontal knife edge by inserting in each hole in turn from A to B, and the time periods are measured in each case. We are inserting the knife edge through each hole and finding the period of oscillation about each hole, starting from the edge end A. The corresponding distances of holes from end A are noted simultaneously. Since the pendulum is symmetrical, the center of gravity will be at a distance equal to half the length of the bar from end A, which we have already seen. And then a graph is plotted with time periods on y-axis and the corresponding distances from end A on the x-axis. So here This is the point, this is the end A, and we are measuring lengths from end A, and these curve corresponds to the value of time periods for different distances from end A. So from end A, we are calculating the time period corresponding to each hole, which we have represented in this curve. Now, the graph will have two parts symmetrically placed about a line parallel to y-axis and cutting the x-axis at G, corresponding to the center of gravity about which the time period is infinity. That is, we have already seen that the center of gravity point corresponds to maximum time period. We have already calculated that in the last class. So as we approach the center of gravity, the time period moves closer to infinity from both sides. Now for a given time period, we can draw a line parallel to the x-axis, cutting the curve at 4 points P, Q, R and S. These points corresponds to the point of suspension, point of oscillation, and point of suspension. We have seen these 4 points in the last class. In the case of compound pendulum, in general case, we have seen these four. There are 4 points in a compound pendulum which corresponds to the same time period. So when we draw a parallel line along this curve, we will get 4 points corresponding to which the time period will be same. 4 points. So the point P will be center of suspension and point R will be center of oscillation. Similarly, point S will be center of suspension and point Q will be center of oscillation. So here the distance PR and QS corresponds to the length of the equivalent simple pendulum. These distances are measured and their mean value is taken. So we know that PR is the length of the equivalent simple pendulum. Last class we've seen that the distance from center of suspension to the center of gravity, which is C here, this distance will be small l, and the distance CR will be L dash. So the distance L plus L dash will give the length of the equivalent simple pendulum, which is capital L. Similarly, from this point of suspension, the distance from S to center of gravity gives the distance small l, and the distance from C to Q gives L dash. So this total distance from Q to S will give the length of the equivalent simple pendulum, capital L. The value of capital L and capital T are then substituted in the equation G equals 4 pi square L upon T square to get the acceleration due to gravity. Now to determine K, the radius of gyration, we consider the points A and B in the graph. A and B corresponds to the point of minimum time period, so that AB equals 2K or K equals AB upon 2. In this graph, in the last class we've seen that for minimum time period, the length of the length should be L equals K. Small l equals K. The small l was the distance from the center of gravity to the point at which the minimum time period is obtained. So this distance. So this is the point which corresponds to minimum time period from the curve. There is no other point below this point for which there will be another time period. So this is the point which corresponds to minimum time period, and the distance from this point to the center of gravity, which is AG. AG corresponds to K. So this distance should be L. This distance L should be equal to K, small k. And again, this distance from G to B, This also corresponds to the same time period for which the time period is minimum, and the total distance AB can be written as 2k, because this half the distance gives the value of k and the total distance gives the value of 2k, and from that we can determine the value of k. Or another manner which we can determine k is, we know the equation k square is equal to L dash, and we know L and L dash here from this graph. L is the distance from center of suspension to the center of gravity, which is PC here, and L dash is the distance from center of gravity to the center of oscillation, which is CR here. So we just take the root of PC into CR. Once k is known, we can determine the moment of inertia of the pendulum using the expression I equals mk square, where m is the mass of the pendulum. Now, in case of asymmetric compound pendulum can be created by just attaching a heavy mass near one of the ends of the symmetric compound pendulum, just to make it asymmetric, or which means making asymmetric means shifting the center of gravity from the center of the bar to one of the edges. So here, in the case of symmetric compound pendulum or the metallic bar that we have seen in the previous slides, the center of gravity was at the center, but here the center of gravity is shifted to one of the sides. We have done that by attaching some mass here. So now the pendulum cannot be oscillated in the inverted position as the mass is attached to B. Now the pendulum can be oscillated only through these points, that is from the lighter end of the pendulum to the center of gravity. And the same way we do the procedure, that is we plot the points with the distance from end A on the x-axis and the time period on y-axis. Here the graph will have only one part, since we are measuring the period of oscillation for only one part of the pendulum. Now, length of the equivalent pendulum can be calculated as the point of suspension to the center of gravity, this distance, plus the distance from point of oscillation or the center of oscillation to the center of gravity. The sum of these two distances, that is PC and QC, will give the equivalent simple pendulum. And again, the radius of gyration can be calculated as the distance from point of minimum time period to the center of gravity, which is AG here, or AC. AG or AC.